uniform flow concept will be required in our every step. I mean, in most of the time, we will be designing the canal by seeing what will be the depth of flow, and in deciding those depth of flow, in computing those depth of flow, we'll be definitely using the concept of uniform flow. And in uniform flow, if we just recall, we studied about the resistance flow formula. And in that resistance flow formula, we remember that we had a resistance parameter, that is the roughness coefficient we call it. So in Manning's equation, that is say n value, and in Chezy's equation that was written as C, Chezy's coefficient C. So that way, whatever may be the name, this particular roughness coefficient depend on the roughness of the channel. So now when we are going for designing a channel, then this roughness parameter is also very significant that we consider, and then we design the canal or channel. Okay. So this aspect will be coming there. Then we studied critical depth or critical flow condition. Of course, critical flow condition will also be required in some part of the design, like that sometimes we may be willing to see that the flow is not supercritical so that the canal will not be damaged, and in those situations we will be requiring the critical flow concept in design of the channel. Well, then of course we studied gradually varied flow and we studied rapidly varied flow. In fact, in canal design, normal canal design, this gradually varied flow and rapidly varied flow concept is not coming directly. But suppose in a canal we have a barrier upstream or barrier downstream rather, then say there will be some gradually varied flow profile forming. And in that case, say for normal condition, when we are designing a canal, suppose we are getting a particular depth in it. Now say we think that there may be some obstruction downstream, and in that case some gradually varied flow profile can be forming, and in those situations what will be the additional height that is required over the computed depth of uniform flow, and those things may be required. And then similarly rapidly varied flow also we may have to see where the hydraulic jump may be forming, and say concept of rapidly varied flow is also required in those situations. Suppose we are narrowing down the canal to a very small width, then sometimes we need to see whether there will be a flux on the upstream, whether there will be a very varied flow just near that say constriction. So those aspects also we need to know. Well, then when we are talking about design of canal, then we should know that there may be channel. When we were discussing about classification of channel, we were mentioning about that part, that is there can be natural channel or there can be artificial channel. Well, now natural channel is that we are getting in the nature, like river, stream, all those things. And in those cases, this concept of canal design or channel design might be coming in some of the issues where we are designing some hydraulic structure, and then there may be some approach channel which is otherwise natural, but we need to maintain some of the conditions there. Say it should not be degraded more, that means there should not be erosion or there should not be say deposition. That sort of condition may come up, and in those situations we will be requiring this concept of canal design in those parts. But in man-made canal, particularly when it is artificial channel, then that means it is a man-made canal when we are talking about artificial channel. Well, that man-made canal, that everything depends on how we design the canal, and that's why for artificial channel, this, or say artificial channel means we call this as the irrigation canal or say drainage channel. Those are artificial channel, and for those situations the concept of designing channel will be coming in a more is more required in those cases. So let us start with say design of canal, and we want to specify at the beginning that canal can be broadly classified into two groups. Well, again, there can be subclasses, but broadly we can classify canal into two groups. Say one is lined canal, like this one that we are showing here. Say this is a lined canal. There are lining. We did discuss about this sort of canal in our very first class itself. So this sort of canal, when we design, then our design concept will be different from that when we design a channel for an unlined situation. Means like that channel or we are showing in the slide here. You can concentrate onto the slide. So the canal can be lined canal or it can be unlined canal. Now when it is lined canal, then we call this as a rigid boundary canal. Okay. So it is a rigid boundary canal. Now by lined or by the term lined canal, what we are meaning is that this canal, when we are constructing, we are providing some lining to the boundary of the canal. Means to the side, say if the canal is there, to the side we are providing some wall, and to the bottom also we are providing some wall. Now those walls can be concrete wall, or sometimes we may decide to provide a, say, wooden boundary also in some cases. And in hilly area, I have seen that some people are providing bamboo lining also. So that way, in some cases, some experimental situation, we may provide, say, plastic also. Like that, so different type of canal alignment can be there. And for if we are trying to carry some very important item, then it can be steel lining also. Well, so like that, canal lining can be of different type. And when we are providing those lining, we are referring this as a lined canal. Well, but another point here, we should know that by lined canal, our objective or design concept is coming like that, that this canal will not be eroded by the flowing water. So that we are completely avoiding in our thinking of design, that this canal is never going to be eroded. And so other requirement will be deciding in the canal design. So now suppose a canal, it may not be lined, but suppose it is passing through a very rocky terrain, and somehow we are making a maybe rectangular or trapezoidal canal through a rocky terrain. Then also there will not be any possibility of getting eroded, or there will be less possibility of getting eroded, because it is, if it is a very hard rock. Of course, it will depend on the composition of rock and how much it is susceptible to water erosion or to weathering, how much it is susceptible to weathering, if it is exposed to water and if it is exposed to atmosphere in tropical country particularly, if those weathering conditions are different. But however, in general, when a canal is made on a rocky terrain, we may consider this to be a type that it will never be eroded. And in that process, the concept of lined canal will be applicable, although we are not providing a artificial lining to such canal. Well, then when we are talking about this unlined canal, means we are talking about mobile boundary canal or mobile boundary channel. By mobile boundary, what we mean that the channel bed and the side can get eroded. Well, it can get eroded. Now, when we talk about this situation that it can get eroded, that means it will depend on various parameters, like what is the flow velocity, how much can be the erosion, what is the type of sediment that is the bed is constituted of, and so, and the bank is. So that way the type of sediment and the saturation condition, all these different aspects will be coming. Well, and again, depending on that, particularly depending on the formation through which the canal is passing. Suppose sometimes it may be a alluvial formation, right? So alluvial formation means the bed material are, say, silt, sand, it is like that. And in that case, it may be more susceptible to erosion. Again, in some case, the canal may be passing through non-alluvial formation, means say clay formation, and in that case, the susceptibility of that to erosion may be less. But again, it depends on, suppose in upstream there is something because of which the canal can carry, or the water flowing through the canal can carry sediment, then we need to see that this sediment should not get deposited into the canal and the path may not be blocked. So all those issues will be coming. Well, with this understanding, then we can have one idea right now that, well, as the canal can be of different type, the design concept for these different types of canal will of course be different. Well, so let us see what can be the design concept of lined channel. Okay, what can be the design concept of a lined canal? So first, let us talk about rigid boundary canal, means which is not mobile. Boundary is rigid, means it is a lined canal. Well, so first point, that canal design, what we mean by canal design, that of course we need to know that the canal need to be designed to carry a given amount of discharge. First, from other criteria we should know that what is our requirement. And what is our requirement means, the basic requirement of a canal is that it should carry this much of discharge. That is the volume of water that need to carry. So we need to design this to carry that sort of discharge. Now when we are saying that we are designing, means what we are basically doing. Well, so discharge is given, and then slope of the channel. Say, when we say that this is our design canal, means what we need to give? We need to say, okay, this is the bed width of the channel that need to be provided. This is the depth of the canal that need to be provided. And of course, we can say that this is the shape. It can be rectangular, it can be, say, trapezoidal, it can be triangular, it can be circular. So different type of shape we may suggest. So that way, our design may involve all those things. And then we can suggest, well, this canal will have to have a slope of this much. But now when we talk about the slope, then we can see that slope of a channel, you can concentrate on the slide, the slope of a channel depends on the topography. Well, that means that slope, we have hardly much scope to play with that particular parameter. Say we need to design a canal in a particular locality or in a particular location to carry discharge from one point to another, then the natural slope or natural topography will guide that what should be the slope. There we can play by a very small amount. Say, for example, if I draw this one, say this is the canal and natural topography is suppose like this. And then we may not design a canal like this and then that and in this way. But we can design a canal by filling up some portion here, then cutting some portion here and then filling up. We can design a channel of uniform slope. Okay. So, I mean, marginally we can change the existing natural slope and we can have our desired slope to some extent. But it is not that we can change the slope grossly. Well, so generally when we talk about design of canal, we do not think or we do not consider that we have enough opportunity to manipulate with the slope. So we will assume that this is the slope, or we will take the natural slope as our slope, and then we will go or we will proceed for the design. Well, then another important point that we were discussing, that is the roughness coefficient depends on the lining material or the roughness of the rigid boundary. So we need to see that what sort of lining we are providing, and based on that we will be deciding that, well, this is our roughness coefficient n. And in some case, well, if we are thinking that by providing a particular type of lining, our, say, roughness coefficient decreases, and we know that when our roughness coefficient decreases, then our discharge capacity or discharge carrying capacity of the channel will increase, because Q is equal to 1 by N then it is coming that A, then r to the power 2 by 3 as b to the power half. So if we remember that formula, 1 by n is there. So if the n value reduces, then the carrying capacity of the channel increases. So in some cases, we may have to change the lining also. In fact, for improving the channel carrying capacity, many a time this side slope or the slope of the canal, the side of the canal and the bed are many a time lined with some finer lining so that we can have better flow through that. Well, then another aspect is the shape of the channel that depends on various constraints. Well, that is, of course, I'm not writing in very elaborately that it depends on various constraints. Now, what can be those various constraints? Shape of the canal. Say, for some situation, we'll have to go for trapezoidal channel. Why? Say, if we go for rectangular channel, then suppose the channel depth coming is quite significantly high. And if we make a vertical cut in a particular formation, then that side or the vertical cut may not stand. There may be slope failure, there may be failure of the side. And so that way, this sort of channels, when there is a vertical cut, when vertical cut is not possible, we need to go for inclined cut, or indirectly this lead to trapezoidal channel. Well, then similarly, sometimes you may find that a triangular shape is suppose better. For some considerations, a triangular shape is better. But when it is a triangular shape, then we can see that, well, when it is triangular shape, then we can see that, just I need to take the pen. Well, so this channel, suppose triangular channel is otherwise better, but we can find that this angle may be sometimes very narrow, and say if sediment deposition take place in this part, it may be practically difficult to clean those things, and that may be one constraint. So I'm just giving you one constraint, but there may be several such practical constraints. And sometimes, say, we feel, okay, circular canal is better. Circular canal, if we construct, it is most economic, or say it is better. But construction of circular canal itself may have lot of practical difficulties. Say, we are trying to construct in a very interior place, and the framework that is required for constructing a circular canal may not be available there. The labor available, or the manpower available rather, may not be having that expertise to make a circular canal. So that way, there may be different situation which force us to take a particular shape. And as I was already telling, that rectangular channel, if we take, suppose this sort of cutting is there, then if this is suppose sandy soil, it will not stand, this will fail. And then if it comes here, if it fails, and if it comes here, this sediment will block the flow and it will create problem. And say we are giving lining, then of course the failure chance is less, but to prevent the failure, the cost of lining that is required may be much high. Rather than that, if we give an inclined shape, then it is otherwise also stable, so lining is not required to support the soil, but support the soil means support the collapse of soil. Erosion resistant, for that purpose we require it, but to prevent the failure of slope, the thickness of the side is not required. So this thickness will be less, and that way it may be preferred. So depending on various constraints, we need to decide the shape of the channel. In some cases, people are trying with channel of this sort. Say this part is circular and then this part is expanding, because this part has cleaning provision, and that's why it may be advantageous. So in some channel we can go for that sort of shape also. Well, so based on all those experience and understanding and the real situation, then we need to decide that what will be the shape of the channel. Well, so once we have the shape of the channel, And at the shape of the channel, we must mention another point, that is the slope. That slope, well, we are saying that it is trapezoidal. Now, depending on the different type of soil, the slope of this trapezoidal channel, maybe this theta, may change. Well, then if all these things are there, say we have the discharge, we now know the roughness coefficient, we have decided that our channel should be trapezoidal or rectangular, whatever it is, which is most advantageous, that we'll decide. And then we are having the slope of the topography also. So after having all these things in our hand, our target will be to design the canal so that we can achieve the highest economy. That is the most economic section we need to design. So our channel should be such that its cost is less. And so that sort of channel, when we design, or this is the very basic concept, when we follow, then the channel shape, whatever we get, we call that as a most economic section. And that particular section, most economic section, is also called hydraulically efficient section, or we call best hydraulic section. Well, so that way, in case of design of line canal, our objective is to design the canal as a most economic section or the best hydraulic section. These are actually just the same name, and or efficient section, right? Different names we follow. But here, okay, we can have some relation. Most economic means, say if we are providing lining, to the canal, then our target, if we try to reduce our cost, then our target will be that, well, our perimeter, because lining means the lining we are providing in the perimeter. Okay, this here we are providing the lining. So if we try to reduce the cost, then this length perimeter should be minimum. So that way we are talking this as a most economic section. But now what is the difference between best hydraulic section or efficient section? You see, most economic section is coming because the cost is less. Now again, if we see, suppose the same area is there, and then to minimize the cost, we are trying to reduce the length of the perimeter. But in that process, we are achieving another objective. See, the resistance to the flow is coming from the perimeter. If our length of the perimeter is more, resistance to the flow will also be more. And when resistance to the flow is more, suppose for the same area, if the cross-sectional area is remaining same, if the perimeter is large, then that is weighted perimeter is large, then resistance will be more, and as such, the discharge will be less. And our objective will always be to carry the maximum discharge, or say required discharge at minimum perimeter, provided area is remaining same. If we talk about excavation, say excavation will depend on the area, sectional area I am talking about. This is total volume, but length is something, and with that length and this area, if we cut the channel, then excavation is coming up. Then excavation will depend on what is the section of the area. If the volume of excavation will be the sectional area multiplied by the length. Now, if this area remain fixed, then this excavation A into L, that volume will remain same, and as such, the cost of excavation will remain same. Now, for the same area, if we can have minimum perimeter, then we are always on the beneficial side. From the economic point of view, that is the cost of lining, and from the flow point of view or hydraulics point of view, that is the discharge point of view. For the same area, discharge carrying will be more if perimeter is less. So that's why we designed the canal with this particular concept, that is the most economic section or best hydraulic section or efficient section. Well, now, but always it may not be possible See, now what will make this best